Hey folks, so welcome back to another lesson on standing or stationary waves. And in this lesson, we're going to look at how to do calculations and apply our knowledge of these standing waves. So just to remind you before we get into it, that remember a standing wave looks like this, and you have nodes where there's a position with zero disturbance and antinodes where you have maximum disturbance. And remember that the distance between a node to a node or an antinode to an antinode is half a wavelength. And by measuring where the nodes to nodes are and counting how many they are, we can actually work out the wavelength of that wave that causes the standing wave. Okay, so let's look at an example of how we use these stationary waves. So a probe picks up a wave reflected from a metal plate, and it's noted that the probe travelled a distance of 5 centimetres between three maxima. The waves have a frequency of 650 Hz. So you can imagine the wave is being given out by the transmitter, hits the metal plate, and it gets reflected. They then interfere to create a standing wave. And the probe, as it moves along, because there's a standing wave, will pick up maximas and minimas. So how do we calculate the wavelength? Well, okay, so how do we calculate the wavelength of this actual wave? Well, first of all, we note that a distance of 5 centimetres was travelled between three maxima. So then if we draw our diagram, notice that if there's three maxima, that means there must be three antinodes. So we draw a wave like this, okay? However, remember that three maximas means there are three antinodes, and then that means there are actually two half wavelengths. So that means 2 times half a wavelength, and all of that is equal to 5 centimeters. So then that means 2 times a half wavelength is the same as one wavelength. So one wavelength is actually equal to 5 centimeters. So notice how it's really important to draw out the standing wave so you can actually work out how many wavelengths there are. Another way they could do this question was they could say that 4 minimas were detected, and then in that case you would draw this, and then you would say, well, if there's 4 minimas, they're actually 1, 2, 3 half wavelengths, and then you work it out from there. So just be aware of that. Now, to get the velocity, it's actually very straightforward. We know that the wavelength is 5 centimeters, so therefore we just have the frequency, which is 650 Hertz. So then we can use the equation speed is equal to frequency times wavelengths, and that gives us the speed of the wave. Now, moving on to a past paper question, we see student is performing an experiment to determine the speed of sound in air. The student uses the apparatus shown. So you've got a loudspeaker with a signal generator, and you've got a tube that's closed at one end, and then a microphone. And the microphone is in a fixed position, the signal generator is switched on, and a stationary wave is formed within the tube. Because what happens is that the stationary wave moves forwards, hits the end of that tube, gets reflected, and then it interferes itself. So that's pretty much how what's happening there. And it says, explain how the stationary wave is formed. So I've kind of given you the answer there, which is the incident or transmitted and reflected waves interfere or are superimposed. Now, this word superimposed, I've not talked about this idea of superposition, but we will come across that later on. So that's why you can use either interfere or superimpose. And that's a very straightforward 1 mark. Now, the second one is at one frequency, the microphone detects a loud sound. The frequency produced by the signal generator is now increased gradually. Describe what happens to the loudness of the sound detected by the microphone as the frequency is being increased to twice its original value. So pause the video and have a wee think. So the answer is the following. The sound will get quieter, and then the sound will get louder again when the frequency has doubled. Now, why does that happen? You're not asked to explain that, you're only asked to describe it. But let's try and dig down and see if you understand what's happening. So the idea is increasing the frequency changes the reflection and interference of the waves. So remember, if you've seen that video of the string being vibrated, when you change the frequency, you actually change the shape of the stationary wave, didn't you? It's not until the frequency has doubled that you then see the next stationary wave being formed. And so that's why when the frequency has doubled, that's when you actually see the next maxima. So this is why, to begin with, the sound gets quieter and then it gets louder as that stationary wave has been reformed. So those are some typical questions that you get asked about stationary wave.